Well, hello everyone, and welcome back to Prep 3.2. So on the prior tab, the one with the essential limit theorem, we had population data and the data for multiple samples. On this tab, we have the population data and the data for only one sample. And you'll see as we go through these tabs, we'll keep taking away the amount of information we have, but still find we can do a statistical inference, which is cool. So here's the population data, and then here's a smaller sample taken from that population. So the problem we have is a car dealer is comparing profits earned at different locations. They conduct a random sample of 30 sales records. In this sample, the average profit turns out to be higher than the population average. Calculate a z-score and then determine the probability of observing the sample mean. So let's frame the problem. So it's probably that becomes higher, so it's probability above x. The case then becomes one-tailed right because you're going above. The function that we're going to use is norm.dist because we're going to calculate a z-score. The problem tells us to, and then compute a probability from the z-score. Okay, so now we're going to look at the mean and standard deviation or expected variability for the population, the sample, and the sampling distribution. All right, so we'll go ahead and begin with the population. The symbols are different in each one. For the population, it's mu for the mean, sigma for the standard deviation. For the sample, it's x bar for the mean, s for the standard deviation. And for SDSM, it's again mu for the mean, because remember they share those two. And then the standard deviation is given by, or what's called the standard error, is given by sigma divided by the square root of n. Okay, so we'll start with population. Mu is going to be the average of all these guys. And for the sample, it's going to be the average of these guys, just the sample. And for the SDSM, it's the same as the population, so it's just that. Done. Okay, and then for variability for the population, it's equal to standard deviation dot p of all these guys. For the sample, it's standard deviation, but this time it's dot s for these. And then for the sampling distribution, then we take sigma, which we've already got over here, so it's going to be equal to sigma divided by the square root of n. Well, we haven't calculated n yet, so let's hold off on this guy until we've done this next line here. We need number of records in the sample, so equals count. Okay, now we can do it. So it's equal to sigma divided by the square root of n. All right. Now, this is really neat because we now have a visual of what we've just done. So here's how to think of it. The red line is the population with its mean at 1843. The black line is our sample. That's the sample data, and its mean is 1977. And then the blue line is the sampling distribution, meaning like if we just kept taking means all day long, like how would they distribute theoretically? And you can see the blue line here. And so the question is, okay, if this is our sample mean, where does it fall in the sampling distribution? That's what we're after. That's what we're trying to calculate. So we're going to keep going. So x bar minus mu is equal to, here's x bar minus mu is this. So that's the difference of the sample mean from the population mean. And then the z-score is calculated as the observed difference from mu divided by the expected variability in the sample mean. Okay, sounds real fancy, but it's really just this divided by the expected variability, which we know for the sampling distribution is this number. And those two will give us the standard error. And then now we can find out, well, what's the probability of getting that number? So first, let's look at what that number is. It gets plotted down here on this graph. And that's a z-score of 1.14. So this bottom graph is the same sampling distribution, but now the other guys have been taken off. So this is just the sampling distribution. And it's been normalized, plotted on a normal curve. And so you get a z-score of 1.14. Where does that fall on a normal curve? Well, it's obviously just over 1 standard deviation from the mean. What's the probability of finding something there is in the right tail, and how much of the right tail is left. Turns out it's 12.63%. Now, this happened automatically, but we can actually calculate it. So this becomes sort of a check on our work over here. So the probability is going to be norm.s.dist. The reason it's S is because z-scores are normalized. That and the cumulative is true. But that's going to be wrong. Remember, we're right tail because norm.s.dist always looks left. So if we want right, we got to subtract all that from 1. And then we get it. Okay, so high probability, low probability, who knows? But statisticians, and we'll see this when we get to the next units, statisticians usually use a cutoff of about 5%, right? In terms of thinking that something's extreme. So something in the green area would be extreme. We're not in the green area, so we're not considered extreme. So a statistician would say, hey, that could happen. It could happen that you have a sample mean out here at the 1977, which translates to a z-score of 1.14, and that would be perfectly reasonable. Okay, so what is the SDSM? It's the distribution of all possible sample means, the size of x bar. Why is the standard error of SDSM less than the population standard deviation? And that is, let's see, because the sample size increases. No, it's not it. Sample mean population, the sample size decreases. Sample size. Increases. Population sample mean approaches population mean. Okay. And then what does the probability of x bar represent? This is a really interesting question because it's the probability of getting a sample mean of 1977 if the true population mean is 1843. That's why we said sample mu equals population mu. We're assuming that they came from the same population. If they came from the same population, then that's the probability that you would see that sample mean. And why do we measure probability in the right tail of the distribution? Because the sample mean diverges to the right. And now we're done with this guy. We'll see you in the next one.